All right, looks like that last group of people I saw coming in came in. So we'll go ahead and get the talk started. My name is Mikey Awbrey. I'm giving a talk on tracking real-time locations with rogue Wi-Fi packets. So this is a pretty bold claim. It's a pretty cool project. So we'll go ahead and dive right in. A little bit more information on introductions here, though. My name is Mikey Awbrey. I am known as Huey on the RF Village Discord, if any of you are on there. I am a little over 10 years now, professional hacker. I do commercial work, government work, other work. I spent 2 years in radar technologies, which I'm only really bringing up because it's quite relevant to this talk and some of the technologies that are being used here. And I'd also like to introduce the device itself. I'm actually wearing 2 of them right now. That's the little blinky things that are right above my badge. You've probably seen several people walking around with these. We are actively using them for a couple of things. You'll see why and what here in a minute. The device itself, it tracks 2.4 gigahertz, and it is a working POC. So it's part of a larger project. The device itself is just a proof of concept, but the proof of concept is fully functional. It actually does some work that we have found to be useful. So we'll start with a technical problem statement. This is what we were trying to solve, why this project came into fruition. And that is that tracking down Wi-Fi devices is something that you have to do occasionally if you're in like the admin world or if you're in secret spaces or anything like that. You find yourself a rogue AP or a rogue device connects to you. You need to be able to track down those devices. Well, the devices, if you've ever had to use them to try and track these things down, are either expensive, hard to use, and most likely both. They are not the greatest of things to try and track down devices with, and sometimes you can spend a very long time looking for stuff. Most of the time, though, you don't have any of that. You simply are told, hey, somebody created a Wi-Fi access point in our area. I need you to go find it and shut it down, and off you go. I see a couple people nodding out in the audience. Off you go. Good luck. I actually had somebody on the bus on the way here. I was talking about this project, and they mentioned that they were re-provisioning all the access points for their company. And they did all of them, but there was one access point they could not find. And it was their own access point. They just had no idea where it was. They just knew that they couldn't find it, couldn't re-provision it. So this is the kind of thing to do it. The idea of this project was to create a low-cost solution with a low barrier of entry to give you guys something that you can use to do this. Is it the best tool in the world? No. But it's also meant to be something that is cheap and accessible. Now, we are going to have to go on a couple of tangents in this talk to make sure that everything kind of comes around full circle. But trust me, everything's coming around full circle. So we're going to start with 802.11 basics. Don't worry, we're not going to go too deep into the protocol. We're not going to go too deep into that whole framework and what it is. But just know that 802.11 is the standard that Wi-Fi devices use to communicate. It's what creates a wireless local area network rather than a wired local area network. They communicate using frames. The concept of frames is the important thing to know to understand how all of this stuff is working. Frames perform all the functions from the management functions from your access point controlling the devices to your devices sending data to and from everywhere. It's all done within frames. So going back, this is an example frame. This is what the frames look like. You can see they've got a header, they've got the body. Different frames will have different structures. The one you're looking at here is an empty data frame. So it's got your destination MAC, your source MAC, your BSS ID. Things like sequence control and the CRC are usually handled by your stack automatically, so don't need to worry too much about it. The important things to take away from this slide are the destination MAC, the source MAC, and the BSS ID. So those are the 3 different things that kind of tell the data where it's going and who it's going to. In this particular example, and the thing you see below there, the destination is like our target device. The source would be set to the device that is sending the data out. And then the BSS ID would be like an access point that's moving stuff around. So just a general understanding of what the frames are, because I'm going to be using terms like source MAC, destination MAC, and null data frames. Those are terms that you're going to hear a lot in this talk. So I wanted to make sure we had that set up front. That way we're all on the same page moving forward. So now I'm going to talk about polite Wi-Fi. So polite Wi-Fi is hesitate to use the term exploit. It's not really an exploit of the 802.11 framework. It is an interesting behavior of the 802.11 framework. The basis of the polite Wi-Fi finding, which came out a number of years ago, there's a bunch of white papers on it, is that every device must send an ACK frame if they receive a valid frame. So this is to make sure that devices know, hey, I sent you data, and it comes back. Similar to in TCP, where you have a handshake where you give data, and then the device acknowledges that it received the data. This is a very similar process. You send a frame to a device. The device says, hey, I got your frame. Interestingly, and what makes this so critical, is that this data, like this valid frame, can come from outside of the network that your station, your device, your targeting is on. So typically, devices will only communicate with each other within the same wireless area network, but these frames don't need to come from the network that you're on. It will just respond with an ACK. So this means that any device can send to a target device a valid frame, and as long as the frame passes the CRC, which is what it defines as a valid frame, then the device must respond with an ACK. It even defines the time period that it has to respond in as 12 microseconds, but most devices don't play nice. So this is a really kind of cool behavior, and it absolutely is real. It's what you have it on. But there are a couple limitations. One of them is power saving mode. So devices will only respond if they are on. And most devices will have a period where they turn off to save battery, right? If devices were on all the time, you would drain your batteries very quickly. There's actually research done with Wi-Fi, with Polite Wi-Fi, where they took security cameras that were made to have like 16 to 20 day batteries, and they were hitting them with these Polite Wi-Fi frames to force them to stay on, and they drained the entire battery in just a matter of a few hours. So power saving mode is a big issue with this. We're already doing a little bit of work on how to overcome the power saving mode. You have to be able to send out a beacon frame with what is called a traffic indication map. That is how devices know that the access point is trying to send them data. So there are ways to kind of overcome this limitation. You can send it a traffic indication map saying, hey, I need you to turn on, and then you can send it the Polite Wi-Fi frame, to which it will then have to respond with an ACK. All of this isn't implemented in these devices yet because this requires you to know the access point as well as the target device. And we're trying to minimize any layers of what you need to know in advance. So this is why Polite Wi-Fi is just considered an interesting anomaly. So if you look at the community as a whole, like the RF Wi-Fi community as a whole, they don't really view Polite Wi-Fi as an exploit because it's just a behavior that is part of the 802.11 framework. It's not really anything. You have to already have a valid frame that is going to a known MAC. The device has to be on, so there's some limitations in it to even work. And then even if it does work, you don't gain any extra information from the target. An ACK frame is extremely simple. I'll give an example of one later, but it only has a single MAC address on it, and that MAC address would be my own device. So if my device sends out a frame to do the Polite Wi-Fi attack, the ACK that comes back has my MAC address on it and nothing else. So the target device doesn't really give anything away. So again, this is just an interesting anomaly. Nobody really thought much of it. So here's where we're going to go on yet another one of those tangents. Don't worry. It all comes full circle, I promise. So we're going to talk a little bit about a technique called trilateration. Trilateration is, and this is one of the only times I'm actually going to read directly off the slide because this is a very important definition. It is the process of using these distance measurements to estimate position. So if you have distance measurements, this is the process of using those measurements to estimate the position of something. Really important. So the way that you get these distance measurements is by using your known factors, which is time, speed, and distance, and the relationship between those three objects. This is where I mentioned my radar background comes into play. This isn't anything too complicated, but distance is equal to speed times time. That's the main formula that we're interested in and going to be looking at that. So when you're doing this, you are beholden to your clock speed of your device measuring it. And that is really important when you are measuring the speed of light. The speed of light is very, very, very fast. Your clock, in comparison to the speed of light, is extremely slow. So that is kind of your biggest limitation is time. You can't control the speed of light. Your time is limited by the clock speed of your device. So your distance measurement is going to be based on those kind of issues. So the longer you can increase that distance traveled, the less problem you're going to have with your distance. We'll go into a little bit more math on that in just a minute, just kind of let that sink in. While we talk about a picture version of trilateration, you can see we're going to talk about the one on the left here, trilateration without Wi-Fi-Polite, how that works. You can see that there are 3 receivers here and a signal source. Those 3 receivers, you have to assume that they know the location of each other, so they know how far apart they are from each other. and their clocks are synchronized to each other. So whenever they get a signal, they can synchronize that data and understand it. When the signal source sends out data, you can get a measurement of when that data gets received. So you can calculate T1, T2, T3, the time from there. You can then use the time to calculate distance and use that to trilaterate. It's a big simplification of the trilateration process. It's a lot more complicated than this, but this is all you really need to know to understand how polite Wi-Fi can enhance this process. There are a lot of limitations to doing it this way, and a lot of the things, if you research Wi-Fi tracking, like using Wi-Fi to locate devices, this is the process that most of them use. You'll a lot of times see these devices that have multiple antennas sticking out in the same location. They're using this kind of a technique to trilaterate. If you're using polite Wi-Fi to do your trilateration, though, you have a couple of main advantages. The biggest one being, if you look, now your source and receiver are in the same location. They're now one device, which means you actually control the source. You know exactly when that source signal came out, which is a huge advantage over just having a random device that you're just getting a signal from. You have no idea when that device sent that data. You just know when you received it. In this situation, you know exactly when that signal came out. And you know the distance between your receivers, just like in the other one, which means you can now calculate from the receivers, you can actually back calculate the clock time that the original signal came out. So this means you no longer have to synchronize your clocks. You can actually use the origin of your controlled source as a way to synchronize the clocks on the attack time. And then you also have now increased that distance because the signal has to go from the signal source to the target has to process data, and then the target has to send data back out. So this is where it diverges from your traditional radar technologies, where it's just a straight bounced signal, much easier to kind of get a distance measurement for. In this case, the signal goes to the device, and the device has to process something and then send back out. This introduces what is called jitter, which is the amount of time it takes the device to process and send back out. In the 802.11 standard, it says that that is meant to be exactly 12 microseconds. That is absolutely not true in the real world, but don't worry, there are ways to solve for it, and we're going to talk about that here in a minute. So this is just a dotted version of this, mostly for people who are watching the pre-recorded version of this talk or who just see the slides. The important things that are here that I didn't talk about at detail is that in trilateration without Wi-Fi or polite Wi-Fi, you have to take the data you've received and you have to line it up. Because if you have a target that's sending out 100 frames a second, you need to know exactly which frame and which timing you're lining up with each different receiver, which involves a lot more processing and time. However, if you're using polite Wi-Fi, it is obvious exactly which frame belongs to which thing. You can back calculate all of that time. So there's a lot of advantages when it comes to trilateration by adding that extra bounce in between, even though you do introduce jitter, which you don't have with the more traditional form of trilateration. And again, I just want to emphasize that increasing distance traveled for the signal increases accuracy. And that's where we were going to talk a little bit about the clock issue. This is your biggest limitation when it comes to accuracy, and this is true no matter what form of trilateration you're using. The best clock speed on an ESP32, at least the ones that I'm using, is a 240 megahertz clock. If you calculate that with the speed of light, that means that a singular clock cycle, that's one operation, is 1.25 meters. So if your device, your target, is 1.25 meters away, and I get that data, if I miss a single clock cycle, I am now 100% inaccurate. If my device is 100 meters away and I miss a single clock cycle, now I'm only 1% inaccurate. So you can see this is why distance and making that distance bigger matters. And polite Wi-Fi gives you some agency over what that distance is. When you're doing the trilateration without Wi-Fi polite, your distance is just whatever the shortest path is from your receiver to the signal. But with this, you have control over it. You really can't get better clock cycles without external stuff. And I don't know if you've ever tried to put external clocks on an ESP32. They don't play nice. They're very difficult to get really good readings on those. So for this reason, you really need to worry about missed clock cycles. You need to make your program, you need to make your system absolutely focused on minimizing any missed clock cycles that you might have. Because again, one missed clock cycle is 1.25 meters of inaccuracy. Now, there's got to be a way to kind of account for this, right? You got to account for jitter, which is going to be that unknown time it takes the device to process. You've got to account for the actual device itself missing clock cycles because you had to process that incoming frame to see if it was the right one you're interested in. And it turns out somebody's actually solved all this. In fact, somebody's kind of done this entire project. Wi-Peep. Has anybody here heard of Wi-Peep? I'm just curious. Has anybody here actually read up on that research? Wow, actually, nobody seems to have known about it. So Wi-Peep's really cool. You should go look it up. A really great white paper on Wi-Peep. They actually made a product which attaches onto a drone some ESP32s and an ESP8266. They send out these polite Wi-Fi frames. They get back the ACKs. They then put that with the GPS on the drone. They fly the thing around, and they claim within a couple dozen centimeters of accuracy, they can locate devices, which is phenomenal. Absolutely amazing. They show the data on how they can account for jitter. They talk about all of this, and they're literally doing exactly what this whole project is about, which is awesome. And again, according to their paper, they were incredibly successful with this. But there was a huge problem. Number one, they put it on a drone, which is really cool, but I want a cheap solution. And drones are not cheap, usually. They're a little cheaper now than they used to be. Number two, they did not release their code. In fact, I reached out to them to ask them about this, and I said, hey, your research is exactly something I want to do. I'd love to talk to you guys and get to know more about this. And they sent back a vaguely threatening email that essentially said, no, we filed a patent, we're commercializing this, back off. And number three, their algorithms and charts that I was talking about that showed they accounted for jitter, they're super informative in the fact that they don't tell you a darn thing. They basically are just like, yeah, we solved jitter. We made a chart. So the approach of using Wi-Peep is absolutely not viable, right? I have no access to their product, I have no access to their code, and I got a vaguely threatening response because I was curious about it. So, you know, we really can't do it. But Wi-Peep did teach me a couple of really important things. Number one, most important thing Wi-Peep taught me is that this idea of using polite Wi-Fi to elicit extra information from the devices via signal analysis is possible. They showed that you can use polite Wi-Fi and the ACK coming back from the signal to do kind of round-trip time calculations, start getting info from it, and have something that works as a result. The number two thing they taught me is that I absolutely, by any means, need to not do anything they did because they filed a patent and sent a vaguely threatening email. So everything that I do, every solution I need to do needs to be completely developed on my own, and I need to make sure that compared to the limited information they do provide, I'm not touching any of their stuff. They've got their baby. I can't touch their baby. But again, it was possible. This is something that works. And somebody out there has proven it, even if they haven't shared how they did. So now I had to break down this problem, right? We have a couple of problems to solve. For one, we need a cheap, polite Wi-Fi implementation. We need to gather, send, and receive data from multiple locations in order to do this analysis, right? Trilateration requires multiple points. I need to actually do the analysis, like whatever that looks like, to do the trilateration to account for jitter. And I need some sort of user-friendly interface, right? All this stuff is great, but if nobody can use it, nobody's going to use it. So from those problems, we're going to break down the gaps that need to be filled and the things that are already solved. So for one, trilateration and other signal analysis techniques, they're already known. Like, I don't need to reinvent trilateration. This is a technique that exists. I need to implement it. I need to find a way to make it work, but I don't have to create it. So this is a gap that I do not need to fill. The next one is a user-friendly interface. I mean, come on, that's entirely doable. Form follows function, though. So I just put that to the back of my mind. We'll figure that out when we get there. We have to have something for the user to interface with. And then finally, gathering, send, and receive data. Well, this is all using the 802.11 framework. That's kind of what the 802.11 framework is made for. So there's got to be some way for that to already be a solved problem as well. Which means that the problem that needs to be filled, the gap that I need to fill, is a hardware solution. Like, I need to find some hardware that can do polite Wi-Fi and is capable of sending and receiving the data that I need it to send and receive. That is actually a gap to fill. Everything else isn't a gap. It's solved. I just need to figure it out. So now we're on to the hardware selection. I'm personally a fan of Espressif. I love their stuff. It's cheap, it's accessible, it's awesome. Their documentation is amazing. And yeah, they're cheap. They also have ESP Now, which is a mesh capability for sending and receiving data between ESPs. It's awesome. And the ESP IDF allows for low-level control, meaning I can send and receive 802.11 frames directly. I don't have to do any weird thing where I'm like trying to change my device's MAC, and I can literally just write an array of bytes and say, send this as an 802.11 frame, and it will say, yes, sir, and send that frame off. So in the end, the actual kit that I chose was the ESP32S2 Solo 2. It is on the dev kit C, and it is $8. I love it. It's what's in these guys right here. It's great. Bought a bunch of them, set them all up. So now we have to break down the problem further. So we have our solution. What do we need to do with it? Problem number one, we need to implement Polite Wi-Fi. Problem number two, we need to implement ESP Now. Well, ESP Now, again, looking at gaps that need to fill. So we're focusing our problem solving on gaps that need to fill. So we're not going to reinvent the wheel. We're not going to start with something that's already solved. We're going to start with a thing that we need to prove that this technology can work. And ESP Now has great documentation. It's implemented, like it already exists. I don't really need to, again, I don't need to reinvent that. I don't need to work with that. I just need to figure out how my solution fits into the already existing solutions that are out there. So that means problem number one is to implement Polite Wi-Fi. There's nothing out there right now that shows you how to do Polite Wi-Fi on this stuff. The papers talk about the technical side of how to do it, but they don't provide any direct examples of here's what you do, here's when you do it, here's how you do it, here's what it looks like. So that is our problem to solve. So now to implement Polite Wi-Fi on an ESP32, we need a couple of things. Number one, we need a valid frame. Number two, we need the target. Number three, we need to set our source ourselves. We need to set our source MAC. We need the ability to send those 802.11 frames, and we need the ability to receive ACKs. You can see here, these are the frames I chose. I chose a null data frame because they're small, they're quick, they're easy. And you actually can throw some data on them if you want, but they are generally just a blank frame that's used to kind of a keep alive signal. And then the ACK coming back, you can see that is an extremely simple frame. It's just got the frame control, which tells you that it's an ACK. It's got how long that frame is going to be there, the MAC receiver, and the end. There's almost no information in an ACK. But we need the ability to do all of this within the ESP32. So the first thing that we need to do in there is implement our first user interface. The user needs to be able to set the target. The user needs to be able to set their source. So we did that using the non-volatile storage, the NVS, on the ESP32, and a serial interface, just a basic serial interface to put the data in. So again, this is our first instance of a user interface implementation. Form follows function. So the function is they need to set the target and the source. The form, easiest, was to just have a serial interface to do so. Also, by using the non-volatile storage, you can reboot your device. So you plug it into your computer, use your serial to set the data, then you can unplug it and plug it into a battery power source, and you don't lose your target, right? It's not stored in memory. It's actually stored on the device. So the next thing we needed to do was implement a frame. Again, I chose a null data frame for this because they are small and easy. They're very quick. They contain all of the details that you need, their destination, your source, and your BSS ID. In this particular case, we actually set the BSS ID and the source to the same thing because we don't know the access point of the target. We don't really care. The target doesn't even really care. We just need to send something valid. And this is a very easy frame to get valid. They're quick to calculate, quick to put out there. The next thing is we need to put the ESP32 into promiscuous mode. And with promiscuous mode, there are a bunch of filters that you can set. So we set the filters in promiscuous mode to read ACK frames. There's a lot of them out there, so you got to have really quick processing for this so you don't fill your buffer. But easy to do. And you know what? While we were looking at putting in promiscuous mode for ACK frames, well, you can set some filters for other types of frames too, so why the heck not? Let's also look at management frames and data frames. Those will tell you if your target's in the area passively. So we now have put the passive scanning feature into this device that has that active scan. So we have both. If your device sends out a beacon, we'll pick that up, and it'll also pick it up if we send out the Polite Wi-Fi. It can do both at the same time, so why not? And don't forget to channel hop. That was a mistake I made early on. Yeah, don't forget to hop through channels. So the next step is to do the next level of user interface, right? The user needs to be able to do something with this data, and I don't want people to have to be walking around with their laptop out all the time reading the serial interface. So I decided the easiest, again, form follows function, is to just throw 2 LEDs on the darn thing. One of them blinks faster if the signal is stronger, and the other one is brighter if the signal is stronger. I have them right here. You can see they're blinking right now. These are actually currently hunting the foxes that are set by the CTF. And you can see I actually have a blink. This blink is just to let me know that it's working. So you've got the power LED on these things. Then you've got this, which is kind of like my software is functional LED. And then once I get a signal, this LED will turn on. It'll actually get brighter if the device is closer. However, in my experience, it is really hard to tell if something is brighter or not. If you've ever actually used LEDs that do that, it's pretty much impossible. That's why I added the second one, which is the faster blink, because that is very clear. You can actually move these closer to devices, and it'll go nuts. It's very, very easy and clear to see when it is functional. And yeah, it started off as just the one LED. I ended up adding the second one, and now we have a user interface that is very clear indication of the RSSI, of the signal strength of their target you're looking for. So I'm going to do a little demonstration of the device. Like I said, I've had them running right here the whole time. I actually think it might be easiest if I do the demonstration by grabbing the video that I have of it. So we'll do that here. Go ahead and finish the talk, and then I'll pull up the video for you guys to do that. Main reason being I don't have foxes nearby for myself to to target. If anybody wants to volunteer a fox, I just need a 2.4 gigahertz device, and we can actually see these things in action. But it's really simple, like I said. Light turns on when you get a signal. Light blinks faster when you get closer. It is not rocket science on that, and it's super easy. The whole point I made it, again, was accessibility. I want this to be something that you have somebody on your team who can say, provision these devices, right? They build the repo, they flash it onto a device, you set the target, and you can hand it off to anybody and just say, hey, play hot or colder. You got a 2.4 gigahertz? Awesome. The next thing I actually need is a USB micro cable. Does anybody here could run to the table that I have? And I got a couple people out here who have been working with me. Somebody could run to the table and grab a USB micro cable off my laptop. I'd appreciate that, or off my desk. So, you know, I want it to be something that you can just hand it off to somebody, and they don't know anything about how this works. They don't need to. They just need to know, hey, if it's blinking, you're closer. And honestly, this has been really successful. We've had a number of people that have come up and been interested in these devices, and I've illustrated it to them. I've handed it off to a few people that I work with who have no idea about any of this code that's in the background and how it's running, and it's a super easy, just they can go out and see it. So again, I'm going to go ahead and do the conclusion. Like I said, we'll do a little bit of a demo here in just a minute. And the conclusion is that the goal was to create a real-time tracking widget for Wi-Fi devices. And that is not finished, but that is well underway. And on the way, we have this proof of concept device that actually does it. The technology there is available, accessible, and cheap, which was all the goals, and it's proven. Do you have the cable? Awesome. And it's proven. So because of that, this is a pretty successful little device, and it's on the way. All the problems that are left are items that, again, when we were doing our problem-solving breakdown and we were looking at it, all of those problems that are left are ones that have been solved in one way or another. So all we have left to do is implement them, right? That's the easy part. Just do it. So if you would like to... I want to set down the microphone, but I don't want to move that thing too much. So you said you had a 2.4 gigahertz device. You got the MAC address for it and stuff? So I'm going to go ahead and unplug this here real quick while I set up a serial reader. Don't you love demos? Aren't they always the best, you know? Always work first time. So no, one thing I can do, it's a little bit of a cheap trick, but I can just look for the DC32 Wi-Fi and start beaconing off of that. But that's not as cool because they're kind of up and around, so I can't like show you that it blinks faster when you get closer because you can only get so close to those. Alrighty, we got serial interface up here. Let me plug it back in. All right, so yeah, here we have a serial output from this device. It's just kind of giving me some data right now. It's essentially just telling me that, hey, I don't see the target. So I just need the MAC of a useful device, and I don't even have my phone on me, so I can't grab that. Let's see. We're connected to DC32 right here. I wonder if I can just grab the MAC address of my access point here. There we go. So 3CE9. So we're going to type it in here, target MAC 3C E9 F7. So one thing that this might not work is this might be the 5 gigahertz band, so we will see. F0483. And I misspelled target MAC. Isn't that great? All right, we're going to fall on plan B here, which is the video demo, because demo gods are not on my side today. So the video, what you're going to see is I actually, when I was testing these devices, I was picking random MAC addresses in my house that I had no idea what these devices were. I didn't even know if they were in my house. I was just going for it. And as a result, I decided to use that as my first fox hunt, was to figure out what these devices were that I was using. So let's see, make sure this is the right video real quick. All right, you guys are going to see the lovely inside of my house as well here. It's going to be great. Real quick question, is there sound coming from the HDMI? There is not. All right, so I will talk through it then. So, see my lovely face here talking to it. So this is in the pre-recorded version. If you're interested in seeing, there's actually 2 videos. One where I actually show the device itself, because you guys can actually come up here after we're done with the talk. If you want to come up, ask questions, see the device, we can talk a little bit more about it. I'd be happy to. So you can see that's there. It's on the breadboard. It's one of the earliest versions of the device, just barely getting it functional. And I'm talking through the fact that I'm getting ready to go and fox hunt stuff in my own house. It's unfortunate there's no sound. I swear I'm giving you the greatest speech of your life. Like, if you could hear me talking on that video right now, you would be just wowed. So I started in my basement. I could tell that it wasn't in there because you can see that it is blinking, but it's not blinking that great. But as I go up the stairs of my house, I'm blinking faster and faster. I actually have no idea where this device is. This is not a directional antenna. This is an omnidirectional antenna. The only data I have to identify this stuff is the signal strength. So, you know, tracking stuff down is understandably a little bit more difficult because of that, but you can see that it is entirely possible. As I'm moving through the house, I'm checking different Wi-Fi devices that I see. You can see it's blinking slower. So that obviously wasn't the device. You can see my children absolutely love to color. I got a little doggy there. Her name's Blueberry. Kids love to color or play. Kids kind of take over the house. You know how that can be. As you can see, I'm getting faster, so I'm thinking it might be my oven. I know my oven has a Wi-Fi device in it, but doesn't seem to be the oven. I don't think that I have any Wi-Fi devices on the counter, but you might as well check. Again, you can use that blinking light. Really easy to see where that is. As I move into this room, it's going faster and faster, so the first thing I go to is my switch. And I also have a device hiding behind the TV, little Google Chromecast thing, and a sound bar, all of which might be the device, but we're not sure. I actually didn't even know how fast the fastest blink was at this point either. I just kind of programmed it and off I went. And then, as you can see, I got really close, and that little blinking light is just going insane. So you can see I've located that it is that little smart speaker right there. So you can kind of see that's how the device operates when it is functioning. So let's get back to the presentation. And yeah, now's the time for questions. If anybody has any questions you want to ask, I'll answer as many as I can. It's a little bit loud, so please do speak up. Yes, sir. I'm sorry, I can't quite hear you here. Let me come forward a little bit. I heard the first part of the question. All right, so the question was, if you wanted to evade this, could you use traffic control to increase the jitter? So if you do that, your device is not responding to ACKs correctly anymore, which will cause all sorts of other issues because your device must ACK any valid frame it receives. That is an 802.11 standard. You would probably end up with connectivity issues in general if you did something like that. I've thought about a number of different ways to try and evade this kind of technique. And an important thing to note about these devices is, for one, that they also do passive scanning, which you can't really evade a passive scan. But for the active side, again, your device has to respond to a valid frame. So if the valid frame comes to you, you need to do that. If you wanted to try and implement something that didn't respond with an ACK, you would likely end up with issues with 802.11 like control, right? Devices would send a packet to you, not receive the ACK, and go, oh, I better send it again, and send it again until they actually receive that proper ACK at the end. Yes, sir. Am I going to release the code? The answer is after DEFCON. So when we are able to do any sort of code release or code reviews, it's currently under review right now before release. I was talking, I think the best place for that to be communicated out will be either on the Discord or in the video description when the actual recorded version of this talk goes live. So if you're not on it, the Radio Frequency Sanctuary Discord, I forgot the exact name of it off the top of my head, but that Discord is a great place. All these guys are on it. They're super responsive. I got to say a big thank you to the admin team. So if you're not on that Discord, get on the Discord. Lots of great stuff being shared there. Yes, sir. Yeah, so the question was that I mentioned trilateration, but I was only doing one device on the video. So that is where I'm specifying this is the proof of concept device. So the full problem statement gets broken down into a number of different steps, and one of them is the fact that there need to be multiple devices communicating to each other, and the data needs to be able to be correlated between the devices. However, in that, I broke down which problems I needed to solve first, which problems don't have a solution. Trilateration is something that exists. It's solved. Well, it's not solved, but there are algorithms for it. There's research on it. But doing polite Wi-Fi on an ESP32 and collecting that data on the same device is not solved. So this is a proof of concept of that part of the chain. So the full trilateration and that scale is not implemented on these singular devices. And again, that's a big weakness that you saw when I was doing the hunt with the device. I only had the signal strength on an omnidirectional antenna. Right, it doesn't do the full-scale trilateration yet, but the point of the presentation was to break down which of those problems are solved, how they're solved, and how this device fits into all of that with a solution for the one missing piece. Yes? So the question was about private MAC addresses from an iPhone and an iPad. So I unfortunately am not familiar with how exactly that protocol works, or how that would work. I know that if it uses 802.11 to send and receive frames, that's what this is. Like these are 802.11 frames that these are looking at and using and manipulating. So if the device is using 802.11 to communicate, that this would affect it. Do iPads and iPhones have something proprietary that is outside of that? I honestly don't know. I don't know if they do not. Somebody's shaking their head. So yeah, so you would end up seeing if it's private MAC. Do you know what that means? I'm not familiar with that. Okay, so apparently with that, if they pick a new MAC address to make a seat, so that actually would be would affect this quite a bit because you set the target MAC, and unless you had something to update that target MAC with the new MAC address, it wouldn't work. Now, I don't know if maybe you could put it into a filter that says all MAC addresses or something like that. Like there's ways that you could attempt to do that, but the way that this device works is once you set that target MAC, that's what it's hunting. So if your device is rotating MACs, then by all means that would evade this device. Yes. Yeah, and I apologize. I'm a big part of the 2.4 traffic right now. So he was just saying that with that was the gentleman who volunteered to use his phone as a 2.4 gigahertz target. He was just saying that's exactly what's happening with his phone. Is it was kind of rotating MACs, and he couldn't even get his own devices to connect to it. So yeah, if we're talking about evasion techniques, rotating your MAC address would be an effective evasion technique, as it would for any Wi-Fi scanner that's looking for a target MAC. If you change your MAC, then it's no longer able to see who you are. Any other questions, or anybody have anything else that they'd like to add? So I do have one more quick little bonus slide. It's nothing too crazy, but I did want to talk about this donkey. So this is a donkey named Maggie, and she is wearing a blanket. So it is a blanketed donkey. Hopefully you get the reference. So I wanted to take a minute to talk about how else this is different than Wi-Peep. Again, Wi-Peep is a solution that supposedly exists, so I do want to kind of cover this real quick. For one, Wi-Peep actually uses two devices that are co-located. This is a very, very, very common solution for this, because it is really hard to send a transmit and then immediately receive that ACK back, because it happens so quickly. This does not rely on co-located devices. And it does not, it can use an arbitrary number of devices even. The idea is to have this be a mesh at the end of the day. So the number of devices don't really matter. They can work together, and it's totally different than their co-located one sender, one receiver. And I have tested, you can in fact, on at least the way I've programmed these, at least the way this works, it will receive the ACK from its own send, its own transmit. It is fast enough to transmit and then receive that ACK. The other thing is they used an 8266 and an ESP32 of unknown type. Ours just uses an ESP32S2, so we're using a totally different hardware base. They also don't mention which one is the receiver, which one's the sender, or how they're doing any of that. So different hardware. And the final thing is that their trilateration techniques relied on drone GPS. The trilateration that we're talking about doing will use round trip time between the devices in the mesh so that they can locate each other in an arbitrary location. The idea is that the user would then pin one of them using a GPS, or even just on an arbitrary map. You could just draw a map on your screen, say this device is here, and then the devices will get the distance to each other and locate devices within that kind of area net that they've cast. So totally different techniques when it comes to how the trilateration's working, totally different set of hardware, and a totally different send and receive methodology. So again, that's my donkey being covered. So yeah, if anybody wants to come up here, see the devices, chat with me, I am more than happy to hang around for a little bit, talk to you guys, let you guys interact with the devices. And yeah, we'll call the talk here. Thank you all for coming, and hopefully you have a great rest of your day.